Hi everyone and welcome to today's video. My name is Emmanuel Olega. I'm a teacher of mathematics and I'm also a software engineer. Today I'm going to be taking you through the introduction to complex numbers. Now this video is a follow-up to a topic that I've already taught. I've already taught about trigonometry. I've already finished the whole topic. So this is a follow-up to it. If you actually haven't checked it out, I encourage you to check through the video. The playlist is here, so make sure you build up on that because this is a follow-up. Some of the things we're going to learn now will need you to have a knowledge of something about trigonometry. So today is for a follow-up of that. So if you're a student of Senior 5 and Senior 6, please get a notebook, get ready to take notes, and please follow and do all the exercises that I can. I'll be doing enough examples for you so that you have a firm grip of this topic of complex numbers. So without wasting time, let's get into today's video. Alright, a look again at our course outline. You can see that we're done with trigonometry. So now we move on to another topic. So about that, I prefer this red brush. So today we're going to look at complex numbers right here. So it's going to be quite some read. I encourage you to get your notebook and get ready to write some few things. And also if you can, there'll be enough examples I'll be going through. I'll be using enough UNEB example as much as I can. Then there'll also be exercises at the end of each single subtopic of complex numbers. Alright, so without wasting time, let's just get into introduction to complex numbers. Alright, so let's begin it off this way. So you may ask yourself a question. So what is a complex number to begin with? So a complex number is a combination of a real number and an imaginary number. So that's what you have to remember. It's a combination of the two. So there is a real number and an imaginary number. So real numbers are numbers like 1, 12.38, negative 0.865. It can be a root 2. It can be a 2 over 3. So basically, nearly every number you can think of is a real number. So whether it's a decimal, a fraction, a root of a number, a cubic root, or even a normal number like this, a whole number, it's still a real number. So basically, any number you can think of is a real number. So how about imaginary numbers? Imaginary numbers are numbers that when squared give a negative result. Okay, that's a little bit strange because I know it's not common. So he says normally this doesn't happen because when we square a positive number or a negative number, we get a positive result. So you remember examples where we had like negative 2 squared and we said that that is also equal to 4, the way positive 2 squared is also equal to 4. So usually squaring a negative or a positive always gives a positive result. But we're saying, but just imagine that such numbers exist, and that's why they are called imaginary. Alright, the unit imaginary number is I. So imaginary numbers are represented using the letter small I. So this is regarded as the square root of negative 1. So the square root of negative 1 is always going to be I. So usually, as you've observed in different numbers, if we end up with a negative 1 inside a root, we actually, the calculator usually give us an error and it says it cannot work that out. So what we're going to do is, remember that an imaginary number is going to be represented by the unit small I, and that is regarded as the square root of a negative 1. So that's what an imaginary number is. So when we square I, we get negative 1. So that means I squared is equal to negative 1. So examples of imaginary numbers are numbers like 3i, 1.04i, negative 2.82i, root 2i, 2 over 3i. So observe how there is an I at the end of each number. That's how we state imaginary numbers. Alright, so let's continue with that. So a purely real number is a number whose imaginary part is equal to 0. So for example, so this is how we usually write complex numbers. We write a real number on the left hand side and an imaginary number on the right hand side. So as you can see in this number, we have a real number adding an imaginary number. So but we're saying that a purely real number is a number whose imaginary part is 0. So this example is a number of a purely real number. So this is purely real because the imaginary part is 0. That's why we have 0i here. I know 0 times I is 0, and then we'll end up with A as our answer. So that's an example of a purely real number. So a purely imaginary number is the opposite. Purely number is purely imaginary number is a number whose real part is equal to 0. So there's a 0 where the a is. So you have 0 there, and of course the answer ends up being bi. Alright, so in summary, we can see that I is equal to root of -1, or we can also see that when we square the I and the root disappears, we have I squared being equal to -1. So a plus 0i, which is an example of a purely real number, is equal to a, then 0 plus bi is equal to bi. So this is how we form a complex number. When you combine a real number and an imaginary number, we get a complex number. So this is how they are stated. We write the real number on the left and the complex number on the, and the imaginary number on the right hand side. So as you can see, the imaginary number has that I next to it. That's how you know an imaginary number. So as you can see, the real part is the a, the imaginary part is the side that has b, and then you can also see that I represents root of -1. So a complex number is simply two numbers added together, a real number and an imaginary number. But each part can also be equal to 0, and that is true because we've actually seen examples of purely imaginary numbers and purely real numbers. So properties of a complex number, we often use the letter z for a complex number. So we can say z is equal to a plus bi. So z is basically a letter we usually use to represent a complex number. So we usually make z to be equal to the complex number. So we have to get used to that kind of representation. So z is a complex number. A and b are real numbers, and then I is the unit imaginary number. So this I is what makes this side the imaginary number side, of which we know I is represented by root of -1. Alright, so let's look at a conjugate of a complex number. So you find the complex conjugate by changing the sign of the imaginary part of the complex number, and it is denoted by z star or z with a bar on the top. So looking at this table here, we can actually see that we have the complex number on this side. The complex number is z, and then the complex conjugate is z star. So if we have a plus bi, the complex conjugate becomes a minus bi. As you can see, we change the sign in front of the imaginary part, so that becomes a minus bi as the complex conjugate of this. So when you want to get the complex conjugate of a minus bi, again we change the sign in front of the imaginary part, and we end up with a plus bi. Then the same thing here, as you can see, this is negative a plus bi, but the rule remains the same. Even in this case where we have a negative on the real, we still change the sign in front of the imaginary, and this becomes that. And then we have negative a minus bi. If we change the sign in front of the imaginary, we also end up with negative a plus bi. So the rule remains the same. We always look at the sign in front of the imaginary part, and that's what we change. So if you're asked to find the complex conjugate of z is equal to a plus bi, the z star value, the complex conjugate becomes a minus bi, just like that. Alright, so if you're asked to find the magnitude of a complex number, the complex magnitude or modulus is the length of a vector from the origin to the complex value plotted in a complex plane. We shall look at complex planes are further within the topic. So if we have this, we have z with bars. So here we're finding the magnitude of z. So z, remember, is the complex number. So we find the magnitude of z, which is a complex number, by root of a squared plus b squared. That gives you the value of the magnitude, and then the answer is in units. So questions. Let's look at this example. Given z is equal to 3 plus 4i, find the conjugate and the modulus. So this is an example of a complex number. So remember, when finding the complex conjugate, we change the sign in front of the imaginary. So z star, which is a complex conjugate, is now 3 minus 4i. Hence we found the complex conjugate. And then if you're asked to find the modulus, remember, we find the modulus by squaring a and squaring b, of which a value is 3 and then b value is 4. So 3 squared plus 4 squared is equal to, that's 9 plus 16, which is 25, and root of 25 is 5 units. And then hence we found the magnitude of the complex number. Alright, so let's look at a unique part. Let's look at addition and subtraction of complex numbers. So to add two complex numbers, we add each part separately. What this means is we add the real part to the other real part, then we also add the imaginary part to the other imaginary part. So if we have this example, if we have this complex number a plus bi adding c plus di, we can see that we add the real part. So the real part here is this, then the real part here is that. So we have a plus c plus, then we have this adding that, b plus d with the I outside. And that's how we add complex numbers. So to subtract a complex number from another complex number, we also subtract each part separately. So this is almost similar, but as you can see, the real parts work together and the imaginary parts work together. So if you have this complex number subtracting this one, we end up with, so we need a minus c plus b minus d with the I outside, and that gives us the value of subtraction. So looking at some questions, so being asked add the complex numbers 3 plus 5i and 4 minus 3i. As you can see, we can add the real parts to each other. So the real parts here are 3 and actually the real parts are 3 and 4. Then the imaginary parts are 5 and negative 3i. So 3 plus 4, as you can see, it's already equal to 7. So 3 adds 4 and the 5 adds with the negative 3i, which of course becomes 5i minus 3i. So we end up having 7 plus 2i as our answer. Alright, looking at question number 3, given two complex numbers, z1, so is the first complex number, is equal to 4 minus 3i, and z2 is equal to 6 minus 14i. Find z1 minus z2. As you can see, this is an example of a subtraction. So we have this subtracting the other. And as we've defined before, we actually see that the real parts subtract each other and the real parts subtract each other. So the first step to do is, the easiest thing is to first open brackets. So we have this, but let's open the brackets here. So when you open the brackets here, it becomes negative 6, and this other one becomes positive 14, because there is already a negative sign here that is affected by this negative sign. So we end up with this. Then we collect like terms. Then when we do that, we have 4 minus 6 and then 14i minus 3i. And then when we put them together, we end up with negative 2 plus 11i, and hence we've solved the question. How about multiplication of complex numbers? So to multiply two complex numbers, each part of the first complex number gets multiplied by each part of the second complex number. So here's an example. So we have this complex number here multiplying this complex number there. So as we said, each part multiplies each part of the other complex number. So we have a times c plus a times di, and that's what you have here. Then we also have bi times c, which is this, and then we have bi times di, which gives us that. As you can see, the b and d end up multiplying, and the i's, when they multiply, give us the I squared value, and that's what we end up with there. So let's look at an example here. So being asked to multiply the complex numbers 3 plus 2i and 1 plus 7i. Alright, so let's solve that. As you can see, we'll have 3 times 1. 3 times 1 is 3. 3 times 7i is 21i. Then we have 2i times 1 is 2i. Then 2i times 7i is 14i squared. But remember that I squared represents negative 1. So that's why this becomes negative 14. And then we have 21i plus 2i giving us 23i. Then when we add the 3 minus 14, it gives us negative 11. And then hence we end up with the answer negative 11 plus 23i. I hope you've observed that most of our final answers are stated in the format a plus bi, and that is really important. This is the most simplified version, and that's what it's desired of most and every number. Alright, let's look at another question. What if you have 1 plus I squared? So obviously when you square something, it means it like two brackets multiplying themselves. So it's two versions of 1 plus I multiplying themselves. So the square of the two. And then when you open the brackets, we have 1 times 1 plus 1 times I. Then we have 1 times I times 1 plus I times I, which is I squared. So we end up with something like that. But remember that I squared represents negative 1. So we end up having something like that. So 1 minus 1 is 0. So we end up with 0 plus 2i. So it's an example of a purely imaginary number because the real part is 0. So obviously this is the same as 2i. So question number 5, we're being asked to solve I squared. So this is an example of a purely imaginary number because we don't see the real part. The real part is actually 0. So this can be written this way. So I squared can be written as 0 plus I squared. And that is because the real part in this case is 0. So if we solve this, we have 0 plus I into bracket 0 plus I. Alright, so obviously when we multiply the different sides, we have 0 values, and then there is I squared. Of course, remember I squared is negative 1. So end up having negative 1 plus 0, of which now we're left with no imaginary part to this. So that's why we're going to put the imaginary part as 0i, of which the answer here is negative 1, of course with a non-existing imaginary part. So the answer is actually now a purely imaginary number, but negative 1 is the answer we're looking for. How about division? So this is where it gets more interesting. So the conjugate is used to help in complex division. The trick is to multiply both top and bottom by the conjugate of the bottom. So now here the conjugate of a complex number is going to play a very important role. So let's look at the question. We're being asked to solve this. So we have 2 plus 3i dividing 4 minus 5i. How do we solve this? As we said, we get the conjugate of the bottom. So what's the conjugate of 4 minus 5i? The conjugate is 4 plus 5i because we will change the sign in front of the imaginary part. So this becomes 4 plus 5i. So we said we multiply both top and bottom by the conjugate of the bottom. So that's how we have this. So 4 plus 5i multiplies both the top and the bottom. So when we multiply them, we end up with that. So remember the rules that we followed in multiplication of complex numbers. So multiply these two values at the top together and the two values at the bottom together. So we end up with something like that, of which when this is simplified, we end up with this. So the I squareds turn into negative 1, and that's why we have negative 15 right here. And then down at the bottom, we can actually see that this 20i and this 20i cancel. Then we are left with 16 minus 25i squared. But the I squared here is a negative 1. So that means this negative 1 is going to affect this negative sign, and we'll be left with positive 25. So that's why we end up with that. So end up having this. So we have negative 7 plus 22i over 41. But now this is not expressed in the form a plus bi. So we're going to split this. We're going to split the denominator to both of the numerator values to have two separate fractions. So we end up having like this. Now this is more like it, and hence this is our final answer. Alright, let's look at some properties of modulus. So we're being told if z1 and z2 are complex numbers, then if we have a bar, inside a bar, if we bring us to find the modulus of product z1 times z2, this can be stated as, it's the same as having the modulus of z1 alone times the modulus of z2 alone. So this is exactly the same when it comes to complex numbers. So the answers are exactly similar. So when you also have we bring us to find the modulus of z1 divided by z2, it's also the same as finding the individual modulus of z1 and then dividing that answer by the individual modulus of z2. So these are similar when it comes to complex numbers. Now this will help simplify your work and lessen the time that you will have to take, because if you don't know this simple property, you may actually end up following a long process. Of course, you may still end up with the correct answer, but that will be unnecessary. So what happens is, in some cases, if someone is given a number like this, if you're being asked to find the modulus of z1 times z2, what someone else may do is they may first multiply z1 times z2, get the answer, and then get the modulus of that answer, which will still give you the correct answer. But this formula allows you to simplify the process. This formula allows you to get straight into working. So this is more of a shortcut, but that works properly. It saves us a lot of time. So even in this case, instead of first dividing this and this before finding the modulus, this allows us to do the work directly. So we end up with that. So if we have this example right here, we can actually get straight to work. Alright, so let's first deal with this first one here. As you can see that this is similar to that, so we get individual modulus of each complex number. So we end up having that. So this, the modulus of this section is that, and then the modulus of this section is that. So we'll get two separate answers, root 169 and root 25, of which root 169 is equal to 13 and root 25 is 5. So 13 times 5 is 65 units. As you can see, we've actually saved a lot of time by knowing the properties of modulus. And then how about for the part of division? So this is exactly the same as that. So when we put those in, and then when we find the individual modulus of each one, we can see that we have that. So we end up with root 169 over root 25, of which root 169 is equal to 13, and then our root 25 is equal to 5. So we end up with 13 over 5 units, and hence that saves us a lot of time. Alright, let's look at a question from UNEB 1991. So this is question number 6a. So I've been told that the total impedance X in an electric circuit which branches Z1 and Z2 is given by 1 over Z is equal to 1 over Z1 plus 1 over Z2. So given that Z1 is equal to 3 plus 4i and Z2 is equal to 5 plus 5i, where I is equal to root of negative 1. I believe we already know that property. Calculate the total impedance Z in the form A plus BI. Alright, so this means that we want the final value of Z to be equal to A plus BI. So it should be simplified at the end. So let's first work this out. So we have this 1 over Z is equal to 1 over Z1 plus 1 over Z2. So when we substitute in the values of Z1 and Z2, we end up having this form of equation. And then we can actually find the LCM of this and that. So the LCM is this. So if we get this value here, divide by this, we end up with 5 plus 5i, and 5 plus 5i times 1 is that. And then when we get this LCM, divide by this, we are left with 3 plus 4i. Then 3 plus 4i times 1 is 3 plus 4i. So that's why we end up with this after finding the LCM. So as you can see, at the top we do some addition, and then at the bottom we actually find the product. We multiply the two complex numbers at the bottom. So when we do addition at the top and multiplication at the bottom, we end up with this as our answer. So that is the value of, so we have 1 over Z being equal to 8 plus 9i over 35i minus 5. But in the question we're being asked to find the total impedance Z. So in the question we're asked to find the value of Z. But what we have here is the reciprocal of Z. So to get Z, so Z is now the reciprocal of 1 over Z. So that means we have 35i minus 5 over 8 plus 9i as the value of Z. But now this is not in the most simplified format. We want this to be in the form A plus BI. So how do we do that? We're going to now apply the format of division. So we're going to divide the top value, divide by the bottom value. So when you do that, remember, we multiply both top and bottom by the conjugate of the bottom, of which the conjugate of the bottom is 8 minus 9i. So that's why we have this. So we multiply both top and bottom with that, we end up with this value here. And then when we open brackets and solve them, we end up with this. So we end up having 65i plus 55 over 29. So when you simplify that and separate this to form two different functions, this is the final answer that we end up with. So this is the real part and this is the imaginary part, and hence we've solved the question. Alright, so lastly I have some trial numbers for you. So find for me Z1 plus Z2 and Z1 minus Z2 in each of the following cases. So I've given you on the right hand side the answers that you should get to for both, so that when you find your answers you can actually compare and make sure you're actually on the right track. So will also be question number 2, where we're being asked to express in the following in the form A plus BI. So that means you just have to end up simplifying them and finding them as the final answers in the form A plus BI. Thank you so much for watching. I hope this video really helped you. Thank you so much for watching this video. Thank you for watching to the very end. I am very, very grateful. I hope this video has blessed you and that it has improved your knowledge of complex numbers. If you really enjoyed this video or if it really helped you, feel free to leave a like on the video. And then if you're new to this channel, I encourage you to join our community by clicking on the subscribe button and then joining it, and then make sure to hit the notification bell so that every single time I upload a new video, you'll get updates on your notifications. See you in my next video.